Let's think about a complex number like this one. And let's suppose that we want to find another complex number that when we cube that complex number, we get this one back. In other words, we're looking for a cube root, right? Well, just by looking at this, I can tell this is 1, right? Because remember, if we want to know if this is one of the roots, all I have to do is cube it and I get this one back. Now let's see if that works then. Let's cube it. U cubed would be equal to, remember how we do this, when we have trig form, we'll cube the modulus. There it goes, 2 cubed is 8. And then we multiply the angle by 3. That's how we raise a complex number in trig form to a power. See? So clearly, U equal 2 cosine 10 plus I sine 10 degrees. That is one of our roots. So we've successfully found one, but the fundamental theorem of algebra tells us there are 3 distinct roots. So let's go about trying to find 2 more. Now, notice what I did here, how I found this 10. I knew that I was going to need to multiply whatever this angle is by 3, because when I'm raising something to the third power, that's what I'm going to need to multiply by 3 to get this back. Well, so I knew that 30 degrees, if I put a 10 here, 3 times 10 is 30, that works. Okay, so let's try some coterminal angles though. So I divided 30 by 3. Let's divide its coterminal angle by 3. So in other words, if I take this 30 degrees and add 360 to it, I get 390, and then divide that by 3 and I get 130. So I took I took the angle originally, 30 divided by 3 and got 10. Then I say, well, let's get a coterminal angle to 30. I added 360 to it, divided that by 3, and I got 130 degrees. So here I had 10 degrees. Another root would have 130 degrees. Let's find another one. Let's find another coterminal angle by adding 2 times 360. So I got 30 plus 720 is 750, and then we'll divide that by 3. Because see, the idea is we're going to multiply by 3, and we want to get back this coterminal angle. So if I multiply 250 by 3, I'll get 750, which is what we wanted, an angle coterminal to 30. But anyway, here's what we have. We have the first root is one we got just by looking. And another way you could look at that is we just took the original angle and divided by 3. Then we took the original angle, added 360 to it to get a coterminal, and divided that by 3. And then our third root was we got another coterminal angle. We added 30, we added 720, 2 times around the circle, 2 times 360 to 30, and got 750. Divided that by 3 and got 250. So we found 3 distinct roots. And when we cube any one of these, we get the result that we're looking for. In other words, we get the complex number that we wanted. Because when we cube each one of these, if I multiply 3 times 10, I get 30. If I multiply 3 times 130, I get a coterminal angle to 30. And the value for cosine and sine will be the same as the value for cosine 30 and sine 30. If I multiply 250 by 3, I get a coterminal angle to 30. So all of these work, all 3 of these work. So let's see what happens. In general, whenever we want to find a root, let's say the nth root of a complex number, we're going to use this formula. We're going to take the nth root of the modulus and then cosine of theta plus coterminal, 360k. In other words, theta and some coterminal angles to theta, and divide each one of those by n. Now, on the previous problem, we took theta, which was 30, and divided it by 3. And then we took 30 plus 360, divided that by 3. And then we took 30 plus 2 times 360 and divided that by 3. In other words, k was 0, 1, and 2. But in general, we're going to have k is 0, 1, 2, 3, all the way up to n minus 1. In our previous example, n was 3, so we went 0, 1, 2. Now this is if we're using degrees. If we're using radians, we would use this one. Instead of plus 360k, we would say plus 2k pi, because there are 360 degrees in a circle and there are 2 pi radians in a circle. So this is what we use. Now let's look at an example. Let's suppose that we've got this complex number and we want to find the fourth roots. 4 distinct roots. 4 distinct complex numbers that have the property that when we raise them to the fourth power, we get z back. So first thing we need to do is convert to trig form. So I need a modulus. And here the modulus would be 16. See, I just squared the real part plus the square of the imaginary part, added them, and then took the square root. Now as far as the angle, we've got the imaginary part over the real part, arctan of that, we get 30 degrees. So we have our complex number here. And what we want to do now is generate our 4 distinct roots. So we're going to use this formula right here. So in place of the modulus being 16, it's going to be, we take the fourth root of 16 and we get 2. See? Fourth root of 16 is 2. Now we take the 30 degrees and we divide by 4. The 4 is because this is the fourth root. So we let k be 0, and we have then, there's no 360k, it's just 0, right? So we take 30 divided by 4. This is our first root. Now let's go for our second when k is equal to 1. So we add 360 to 30 and then divide by 4. Then we have k equals 2. This is our third root. Now we add 2 times 360 onto 30, divide by 4. And then finally, the grand finale, k is equal to 3. Let me make that. So now we have that k is equal to 3. And we have 30 plus 3 times 360 divided by 4. So this is an example of how we find the 4 distinct roots of z. Notice we just use this formula and we're just letting k be 0, 1, 2, and 3. If this had been the fifth, it would be 0, 1, 2, 3, and 4.